So next we look at GoogleNet, which is 22 layers, which is even more deeper, little bit more deeper. So 22 layers, and the architecture is quite different because they use this Inception module, so this is the Inception module. So Inception module, basically it uses various convolution, for example, it uses this 1 cross 1, 3 cross 3, 5 cross 5, and 3 cross 3 max pooling. So we'll come to it. So it uses this Inception module and it repeats this Inception module. For example, all of these are Inception modules. So it has 9 such Inception modules. So basically it has this Inception module which is repeated again and again. And it doesn't have any fully connected layer. And it has 5 million parameters only, much lesser than AlexNet, which has 60 million. So AlexNet, which has just 8 layers, has 60 millions, whereas this one, GoogleNet, has 22 layers and just 5 million parameters, so much lesser. And actually it is also very, very less compared to VGG, which has more than 100 million parameters, right? This is just 5 million. So 20x lesser number of parameters. And it also was one of the winners in this competition. And their most important contribution is this Inception module. So what they do is design a good local network, and then they stack this module on top of each other. So like for example, this is one of the Inception modules and there are 9 such modules. So the main idea is design this local Inception module well, and then you can just stack them. That is their idea. And what is Inception is, the basic idea of Inception is that we apply parallel filter operations on the input from previous layer, and the main idea is to use multiple receptive field sizes for convolution. For example, if you see, it is using 1 cross 1 convolution, 3 cross 3 convolution, 5 cross 5 convolution, and 3 cross 3 max pooling. So it is taking all of these. So it is doing 3 cross 3 filtering, 5 cross 5, 1 cross 1. Will come to what 1 cross 1 means, and 3 cross 3 max pooling, and it takes all this filter output and concatenate them. So you are looking at the image at various resolutions basically, or at various receptive field sizes. So 3 cross 3, 5 cross 5, 1 cross 1. So all these various receptive sizes you're looking at, and then we are concatenating all of them, and that becomes the Inception module. So this is a naive Inception module. What we'll see is that it increases the computation very much. So there is some basically 1 cross 1 convolutions are used. For example, all these things, these extra 1 cross 1 convolution is used to reduce the number of parameters or computations. But apart from that, it is this and that is similar only, apart from those 1 cross 1 bottleneck layers. Now we'll look at what is this 1 cross 1 convolution. So as the name suggests, it is doing 1 cross 1 convolution. So for example, generally 3 cross 3 means it will look at this, right, a 3 cross 3 window, and then and of course it looks at in the 3 dimensions. So if you have 64 layers, actually the number of parameters or this is required, like you basically have this, you're looking at something like this. So if it is a 3 cross 3 filter, then it is 3 cross 3. So then the number of weights is 3 cross 3 cross 64, right? But what this 1 cross 1 convolution means is that you are just looking at 1 pixel. And then, but you're looking at all the channels, like all the 64 channels. So what you're looking at is 1 cross 1 cross 64. And that is your filter weights. So all you're doing is you have a filter which is like this, 1 cross 1 cross 64. And you're taking the inner product. So which is nothing but you're looking at 1 pixel location, XY pixel location, and for that particular XY location, you're taking all the input, all the channels, right? So that becomes a vector, 64 dimension vector, and you have the kernel also 1 cross 1. So you do an inner product with that, and that will give you 1 channel in here. So, and there are some 32 such 1 cross 1 filters, so you get 32 such channels. So each filter has a size of 1 cross 1 cross 64, and it performs a 64 dimension dot product, right? So because you're doing this, right, 64 dimension, and that will give rise to the pixel here in the first layer, in one of the layers. And if you have using 32 layers, you get 32. So by doing 1 cross 1 convolution, this image size, spatial size of course will remain same, right? 56 cross 56. I mean, whatever the size, it remains, because there are no nothing you're doing. You're not doing striding or all those things. But what happens mainly is that the number of channels you can reduce from 64 to 32 or even lesser. So in some sense, it is actually doing the dimension reduction. So it is doing this dimension. So it is like 64 dimension to 32 dimension, 64 channels to 32 channels, 64 feature map to 32 feature map. So it is doing dimension reduction. So that is the idea of 1 cross 1 convolution. So it preserves spatial dimensions, which is 56 cross 56, but it reduces the depth, right? I mean, it can increase also, but generally we are interested in reducing. So it projects the depth. So depth goes from 64 to 32. It projects this dimension, this channel dimension, to lower dimension, and which basically means that you're combining the 64 feature maps to get 32 feature maps. So it's a dimension reduction along the feature direction. So that is what 1 cross 1 convolution is doing. So basically it is for reducing depth, which will reduce the computation. That is what this 1 cross 1 convolution is doing. So now let's look at, as we have said, this has too many computations. So let's look at how much computation it has. So the problem is there's computational complexity. So now let's look at where it arises from. So for example, let's consider this, so that we have input which is 28 cross 28 cross 256 channels. And let's say we have this filters, 1 cross 1 convolution, but 128 such filter, 3 cross 3 convolution, 192 such filters, 5 cross 5 with 96 filters, and 3 cross 3 pooling. Now what will be the output size for each of them? So for example, when we apply this filter, so what do you think? So it will be, spatial dimension will remain same. So it will be 28 cross 28, and the channels becomes 128, right? So it will become 28 cross 28 cross 128. This will become, because let's say it is using stride 1 and all, padding of 1. So again, spatial size will remain same, 28 cross 28, and the number of channels becomes 192. So like this we can compute. So what is the output size of 1 cross 1 convolution with 128 filters? It is this. For all the other, we can find out the output sizes, and this will be this, right? And now we want to find out, and after filter concatenation, what will be the output size? So I am concatenating all of these. So all these channels, 128 channels, 192 plus 96 plus 256. So these many, so is the total number of channels. So this is the 28 cross 28 is the spatial size, but 672 is the number of channels this will have. So we can see that by doing this kind of things, the number of channels will always increase, because if there are 256 channels here, after doing pooling itself we'll get 256, and all the other operations will only add. So the number of channels is only going to increase from whatever the input is. This is one of the problems, and this is what we want to reduce. And the other is computation involved is also very huge. That also we want to reduce. So if I look at the total number of operation, convolution operation and multiplication operation, then this is these many million operations are required. It's a huge number. So we need to reduce it. And let's see how this is how we came to this number. So if you look at this 1 cross 1 convolution with 128 channels, so how many computation are required? How many multiplications are required? So you're applying a 1 cross 1 filter. So 1 cross 1 across 256. So 1 cross 1 across 256 channels. So this many dot products you will do, but this will only produce 1 pixel in this, right? 1 pixel is produced by 1 cross 1 cross 256 dot products. Sorry, not dot products, multiplications. And then we have to produce all the pixels in the output, which is 28 cross 28 cross 128. So these many computations. Similarly, for 3 cross 3 convolution, for even producing one pixel in this image at the output, you require 3 cross 3 cross 256, right? So 3 cross 3 cross 256, and to produce all the pixels, so many pixels are there, you need so many computations. For 5 cross 5 convolution with 96 channel, first of all, to even produce one pixel in this convolution output, you require 5 cross 5 cross 256, this many multiplications, and then we have so many pixels, so like that, so many operations, and it's a huge. So we want to reduce the number of operations. And also pooling layer preserves feature depth, which means that the total depth after concatenation can grow at every layer. So as we have said, pooling layer itself is preserving this. So, and we are adding more such channels here, so it's always going to grow. That also is a negative thing, so we want to reduce that also. So for these, for reducing computation and for reducing the number of channels at the output or depth, we are going to use this 1 cross 1 convolution at multiple places. So the solution is use this bottleneck layer or 1 cross 1 convolution to reduce feature depth, which will reduce computation. And how it is done is you introduce this 1 cross 1 convolutions here. So just before this 3 cross 3 convolutions, because we are introduce this 1 cross 1, before 5 cross 5, 1 cross 1, and after pooling you introduce this. And with this, it will actually reduce the number of computations. So this is again an exercise which shows that if you introduce this 1 cross 1 convolution, this 3 extra, then it will reduce the total number of computation, and the computation becomes this compared to what it was earlier. So earlier it was 800 million, now it has come down to 300 million. So like half, less than half operations. Okay, so compared to this many operation for naive person, this bottleneck has reduced. So it has definitely has reduced the number of computations. And these are like, you can actually go through these things like the same kind of computation we have done before to do that. And another thing is that also it reduces the depth after pooling layer, right? So earlier we have seen it was like 600 something, now it has reduced it. Because this, as we are saying earlier, in the naive Inception module, this pooling layer will always have the same number of channels as input, but using this con by 1 cross 1 convolution, you can reduce it. And therefore, the total number of channels can actually be less than this also, input also. But generally, as we go deeper, the number of channels only increase. So that's why it has shown more. But by using all this 1 cross 1, we can actually reduce also if you want. So this is the advantage of doing this 1 cross 1 convolution or bottleneck layers. And that is the Inception module, right? Basically, this is the Inception module. And then we stack this Inception module on top of each other. So 9 such Inception modules. And that give rise to this GoogleNet. So that is the idea. So design the Inception module well, and then stack many of them one after another. So that is the idea of GoogleNet. And there is some stem network, like before we get to the inception, it goes through some convolution pooling, and again 2 such layers of convolution pooling before it goes into the Inception module. So this is the input size, input. And this is the stacked Inception modules, and this is the classifier output. So this fully connected layer has been removed. Actually, one fully connected might be there to match it to the number of output channels that we have, number of classes we have. For example, let's say we are using 1000, if there are 1000 classes, then we need to bring the number of nodes to 1000, right? Then only it can go to 1000 classes. If it has 100 classes, then we need to bring it to 100. So actually there is one fully connected, but that is just to bring it to the correct number of nodes, not for training as such. And these are some auxiliary classifiers, which also does the task of classification. And the main goal is that this layer is too deep, like 22 layers are there, which makes it very deep, which makes it very difficult to train. There is some problem called vanishing gradient. The gradient, generally, when we do error backprop, the gradient needs to backpropagate, right? Propagate from the output to the input. Now, if there are 22 layers, there's very good chance that the gradient will not propagate. So to avoid that, there are some auxiliary classifiers, like from there, and we start gradient descent from here. or from here like that. So this will reduce the problem of gradient descent to some extent. So for that, there was some configuration has been used, 1 cross pooling, then 1 cross 1 convolution, so 2 fully connected plus softmax. But notice that this is, though here the fully connected are there, but first of all, this network, auxiliary network, is only during training. During testing or inference, we will not use them. We will get the output from here only. So these networks will not be used during inference. This is only for training to remove this gradient, vanishing gradient problem. Okay. So total 22 layers are there, and how to count? Because we count like this. So first of all, this is 1, 2, 3. These are the convolution layers. Then each of them, there are like each inception, there are 2 layers. Like if we see before, 2 layers. Yeah. So 2 layers. One is this layer, another is this layer. So 2 layers is there. So each inception contributes to 2 layers, and okay, so each inception layer contributes 2 layers, and there are 9 such inception layers. It makes it 18, and then 19, 20, 21, and there is fully connected 22. So like this. So it's a 22 layer network. And so 22 layer networks whose main backbone is this inception module, and there is no fully connected layer apart from mapping it to the correct number of classes, and it has 12x less parameters than AlexNet and 20x less than VGGNet, or even more actually. So it is very, very efficient in that terms, and it also gives very good performance. Okay. So now we come to the last network that we want to discuss, and it's a huge, you can see the jump. So it is like 22 layers, and this is like 152 layers. So huge jump in the number of layers. So it's a revolution of depth, and this is what we look at, ResNet or residual net. This is called ResNet or residual net. So it's a very deep network, and whose main contribution is using this residual connection, So just like the heart of GoogleNet is the Inception module, same way the heart or the basic material for residual network is this network, which is then repeated again and again. And especially you look at this residual connection. This connection is called as the residual connection or skip connection. This is the main block, and you just repeat it again and again. For example, this is what this represent, and you repeat these blocks again and again, and then you get this huge and deep network. So it's a 152 layer model for ImageNet, and it gave a very good performance. Like even compared to GoogleNet, it did much better, and it won all the competitions in that year. So now the question is, why people did not do like this before? Like if we just take a normal convolution layer and then make it deeper and deeper, will it be fine, or will we encounter some problem? So why do we need this residual block? So what happens if we keep on stacking deeper layers in a plain convolution neural network without this residual connection? What happens then? So this is what has been shown. This is like training error and testing error for a layer which is like for a 20 layer network, CNN network, and this is like 56 layer. So again, this is for test error. So what do we see? Actually, what is strange is this, even the training error for the 56 layer is higher than the training error for 20 layer. Actually, we usually see the deeper the thing is, more complex a model is, at least the training error reduces. The training error should have been lesser than the 20 layer. But here the training error is also large. Test error can be large because it can be overfitting and all, but at least training error should be lesser for a more complex model. But we see that the training error is also more. So that is what, like why the training error is more. Test error can be fine, but why the training error? So that is the thing. So basically the main idea was it was not able to train it. We were not able to properly train such a deep network because of the gradient, vanishing gradient problem. That is the main problem. So it's an optimization problem, and deeper models are harder to optimize. And ideally we should have performed well, should be able to perform at least as well as the shallow model, at least during training, right? That is what. And there are some construction, if you can, so for example, let's say you have 20 layer and you want to make it 50. So actually you can map 20 layers from this network to 20 layers at random position in the other 50 layer network, not random position, into like proper, like you can do some proper sequencing, map it, and the remaining layers you can make it an identity layer. And with that, at least it should perform as well as the shallower model, but that also was not happening properly. I mean, of course, after that you have to train, but that also was not happening properly, and that is mostly because of vanishing gradient problem. So to solve this vanishing gradient problem is this residual network has been introduced. So one way to see why it can reduce vanishing gradient problem is actually to see this network itself. So each of them is a residual network. So each of this is a residual block. So each of this. So what we see is this connection. This is called skip connection or residual connection. This is the connection, skip connection. So we can easily see that the gradients can actually flow through this skip connection like this. So, and then it can go anywhere we want. And so we can see that the vanishing gradient problem is not a big problem here. And that is one of the biggest advantage of this residual network. And the other advantage is that we only need to compute the residual. Okay. So for example, this is a plain network, like plain CNN network, which has this convolution, ReLU convolution. And let's say it is producing this function h of x. But in residual block, what happens is we have this input x. There is a residual connection which directly goes to here. And then whatever, let's say this network, convolution and ReLU, if it is producing f of x, then after at the output, since we are adding this x again, it produces x plus fx. Okay, so basically my h of x, whereas here I was directly supposed to go from x to h of x, now I am going to x plus f of x. So in some sense, this is nothing but the residual, right? Because f of x is h of x minus x. So we are learning the residual. So we are just learning the residual f of x instead of the whole function. We are just learning the residual. And for example, if my f of h of x itself is identity, then I need not, I mean, all the weights will be easily 0 and I will directly get x. And if my h of x is close to identity, then also the residual will be small. So that is the idea. So instead of learning a very complicated function, we just learn the residual h of x minus x, which is easier to learn. So that is one of the advantage. So basically two advantage. One is like this gradient, gradient can flow back without vanishing. And the second is we are only computing the residual and not the whole function. So these are the two advantage. And the full architecture is nothing but we stack this residual block. So this is a residual block. So we stack this residual block on top of each other. That's all we do. And every residual block has two, this is the first and this is second, 2 cross 2. 2 3 cross 3 con layers, that is the structure. And periodically what we do is periodically we double the number of filters and downsample spatially using stride 2 in each dimension. So for example, here we can see this sign, this divide by 2, which means we are doing a stride of 2, which will reduce the spatial size, right? So whenever we do stride, whatever the spatial size, it will reduce by half along both the horizontal and vertical direction. And we are increasing, at that time we are increasing the number of channels. So here the number of channels was 64. So we reduce the spatial size by 2. 2 means along both dimensions, horizontal and vertical of the image. But we are increasing the number of channels by twice. So that is the thing that is followed. So for example, here all these are like residual blocks. Here we are reducing the size of the image by half, but we are increasing the channel by twice. Then you keep on repeating again and again. And again at some point you reduce the size by half, but increase the number of channels by twice. So from actually from 128 it became 256, then 256, 512, like that. It is going like that. So more or less this kind of grammar is being followed, a rule is being followed. There is some additional con layer at the beginning, for example this. And again, there's no fully connected layer apart from the layer needed to map it to the number of classes. So this is more or less the architecture, and you can have different number of layers. We need not have 152 only, it can be 50 layers, 100 layers, whatever we want. So total depth, these many versions were there when they showed result for these many versions. But more or less, this is the construction that we follow. And even and like for very deep networks, we can also use this bottleneck layers like 1x1 convolution. So here we need two 1x1 convolutions. For example, let's say we want to reduce the number of channels to 64 so that the computation reduces, so it becomes 3x3 equals 64. But then ultimately we want 256, right? Because this is the input and this input is getting added, like whatever this x, I'm adding this x. So the number of channels here should be same as the number of channels here. So if I reduce it, again I have to increase it. So again I'm using 1x1 convolution. But by using this, the total number of computation is less, and that is what is used, similar to GoogleNet for larger network. And for ResNet training, batch normalization has been used after every conv layer. So this is a normalization mostly for handling. So basically kind of this is nothing but you subtract the mean and make the variance equal to standard deviation equal to 1. So that is the more or less. So you take a batch of samples, find the mean, subtract the mean, find the covariance, divide by the covariance. So it becomes mean 0, standard deviation 1. So that is what this is doing. And this is again to reduce so that it doesn't blow up and all, the activation doesn't blow up and all those things. So Xavier initialization, this is how you initialize the weights of the network. So this is some technique which makes it very stable so that you can converge faster. Because again, stochastic gradient descent with momentum, this is some technique, stochastic gradient, because we cannot take whole training data, but we are taking some random batch of it. So that is why it is stochastic gradient descent. Learning rate, as we have said, how much step to take along the gradient descent direction. Mini batch size, how many images, how many patches we are going to take, and weight decay and all these are regularization technique. Dropout was not used. So anyway, these are training details for ResNet. And this is the kind of experimental result that was that they obtained, that it was able to train very deep, like 152 layers. And so even deeper layers can be trained like that, and it again performed very, very well. So this is overall what we covered. So we covered all these, and especially VGGNet, GoogleNet and ResNet, these are all widely used. VGGNet is very generalized and can be used for many purposes. ResNet is very deep and all. ResNet, this we're saying current based, this may not be the current based, but because there are many developments after that. For example, there are also dense connection where once you extract some features, you can actually for the remaining layers, you can pass on those features and you can concatenate them. So there is something called DenseNet, which is also very good. So there are some other, like even after ResNet also, there are many developments. And the trend is towards deeper networks, and also this layer skip connections, dense connections, all those to increase gradient flow and all. There's still, CNN is more or less settled kind of, but still there is something going on. And also you can do depth versus width. So depth is as in ResNet, width as in GoogleNet, and maybe you can do combination, and there are all many versions like that already there. So these are more or less, and this is what we have covered in this session. So we looked at object recognition, and these are the various architectures for object recognition. LeNet, of course, is very, very preliminary. It was also not the best performing at its time, but AlexNet is what started the revolution. So it has this 8 layers, but VGGNet does even better with smaller filter size, 3x3. GoogleNet uses this kind of parallel receptive field, combines parallel filters, also perform very well. And ResNet actually uses this residual connections so that you can go deeper and deeper. So this is what we have seen in object recognition. So our next session will be on object detection.